Hey class, and welcome back to Physics of Everyday Life. I want to give you guys sort of an abridged look at Chapter 7. So we're going to talk a little bit about wood stoves, about heat transfer mechanisms, and wrap things up with a little bit of a discussion about what are greenhouse gases and what is the greenhouse effect. So I'm going to break this kind of Chapter 7 lecture into two shorter videos. But in these two videos, we're going to be tackling 5 basic questions. We're going to talk a little bit about thermal energy and heat, understanding what they are. We're going to talk about how wood stoves specifically produce thermal energy. Get excited. You get a free sort of bonus lecture about chemistry here in Physics of Everyday Life, because chemistry is really just the physics of chemical elements, right? And then we are also going to get into looking at kind of the pros and cons of stoves and how they work, and then end up talking a little bit about how stoves transfer energy through a room, and then kind of a bonus question will be about unpacking what is the greenhouse effect. So first of all, I want you to take a minute and think about what is thermal energy, how would you define it, and what is heat, how would you define that? What are the similarities and differences of the two? How do they compare and contrast? So pause the video if you haven't thought about this already. Hopefully you paused it and thought about it. So here we go. First of all, thermal energy is the disordered energy of an object. So if you remember, I told you that there's a thing called kinetic energy, the energy of motion, right? So when we talked about kinetic energy of, like, say, my flying tennis ball here, we're talking about the kinetic energy, the energy of motion of the ball, where all the particles of the ball, all the molecules and atoms that make up the ball, are moving together in the same direction. Thermal energy is also actually a form of kinetic energy, but it's very disordered. All of the particles and elements are all moving in different directions and not in a uniform direction together. But thermal energy is the energy of motion on a small scale, and it's directly related to the temperature of an object. So the more thermal energy something has, the higher its temperature will be, and the faster its particles are moving. So on a hot day, the air is actually moving faster than it is on a colder day. And so again, this is responsible for temperature. Heat, on the other hand, while we think of it a lot of times as being the same thing as thermal energy, it's not. It's actually the flowing of that thermal energy between objects. All right, so when you feel heat, for example, maybe standing out in the sun on a summer's day, what's happening is thermal energy is being transferred to you, and you feel that flow of thermal energy. Or imagine you grab a cold beverage, right? Like here, my little seltzer water. If I grab this and hold on to it, it feels cool, all right? Because what's happening is thermal energy is flowing from my hand into the can. I'm actually giving thermal energy to the can. So heat is moving from my hand to the can as I warm it up and touching it. In fact, anytime I'm drinking a cold drink, I want it to stay cold. I try to minimize how much I touch the can. Otherwise, I will be heating up the can, which then, in addition, will heat up, transfer thermal energy to the drink itself, and it won't be as cool, which is not that cool. So anyway, again, heat is the flow of thermal energy, and it's caused by a difference in temperatures. So heat will naturally always flow from a hotter object to a cooler object. It will naturally flow because of a temperature difference. So the next question I want to talk a little bit about is, how is thermal energy produced? How do wood stoves produce thermal energy? What do you think? Where does it come from? Well, if we think about conservation of energy, it must come from some other form, right? And where it comes from is actually chemical potential energy. So there's a little bit of chemistry to fully understand this, but it's really cool. So I want to unpack it for you a little bit. What happens is fire is able to release the chemical potential energy stored within wood, or whatever the fuel is, wood or coal, or even gas in a gas fireplace, or oil in an oil lamp, or something like that. And so it's able to actually take these complex molecules of wood, add air, and break down and rearrange the actual chemical bonds, creating new chemical elements which have less overall chemical potential energy. So they take away the chemical potential energy as these bonds are reorganized, releasing that chemical energy in a different form of now thermal energy. So we're going to have to define a few things to make sure we understand this. But what's happening is molecules, which are multiple elements bonded together, molecules which are bonded by these chemical bonds are actually broken apart and rearranged, and the breaking apart of those chemical bonds has the potential to release energy. All right, so burning is this process where bonds are being rearranged and energy is being released. So if you take wood, which has a lot of complex bonds in it, a lot of chemical potential energy stored in those bonds, if you add enough heat for those bonds to be rearranged, then you're going to get out thermal energy in the form of heat being transferred away from the wood to something else, and then some leftovers. All right, so again, just to drive this idea home, I brought some very fancy demonstration devices. I have some matches here. So if I strike this match, I'm going to add some energy to start the reaction to happening. And so I use friction to add energy. And now I'm actually burning my little stick here. I'm destroying it, breaking its chemical bonds, allowing those to rearrange, and it's releasing thermal energy. And while my match will burn out relatively quickly, I'm going to light my little birthday candle I have here. And so now we can watch. Now I have my birthday candle here. And so now there's enough thermal energy there to cause the chemical bonds to break down and rearrange. But I no longer am burning wood. I have a different fuel source, a different fuel with different types of bonds and molecules in it, although it's similar, that are being rearranged. And that's the fuel coming actually from the wax. There's oils and things in the wax that are now the fuel burning, and the wick is just the place where that burning is able to occur consistently. All right, so let's just make sure we understand some of the terms involved in what we're watching here. So we have molecules, okay? So again, a molecule is just multiple atoms bonded together, joined together by little chemical bonds. So again, you can think of those bonds as like little sorts of springs that are attaching these chemical elements together, and those springs have potential energy in them, chemical potential energy though here instead of elastic. All right, the chemical bond, that's again the chemical force, which if you want to know more about, take chemistry class, but that's the force that's kind of holding those individual atoms together. And then the bond strength is something that you might hear us talk a little bit about, and you might read a little bit about in the book, but that's a way of quantifying how much energy is stored, how strongly bonded your different atoms are together. And then when we talk about chemical reactions, reactants are the things you start with, the molecules that you start with, and then the products are what you get out of your chemical reaction. So I'm going to give you the example of burning wood, which again is similar to what's going on here with my candle, but instead of wood I have this wax, right? All right, so now let's talk about chemical reactions in a little more detail. So again, chemical reactions are the breaking down of bonds. So to break bonds down, they're not going to just break on their own usually. So you need to do some sort of work or add some sort of energy to cause the bonds to start breaking. And then they'll, once they're broken, they have the freedom then to form new bonds. All right, and if those new bonds are stronger than the old bonds, you're able to create or release chemical potential energy in the process. You're changing the amount of chemical potential energy. All right, but again, to get this started, you need something to begin the process. You need to start by breaking those bonds somehow. And so you need to add some initial energy, which is oftentimes referred to as the activation energy. So again, if we go back to the example of a simple match, these matches are not going to just burn on their own. They need some activation energy to get them started. And so that activation energy in this case will come from friction. I will apply a friction force to them, rubbing them against the little black strip on the back of this, and that friction will produce a little bit of thermal energy, enough in fact to start the chemical reaction. Now if I just barely rub it on here really gently, there's not nearly enough thermal energy, but if I rub it hard enough, I produce, oh, not enough. I produce enough thermal energy to cause the reaction to start occurring. And in fact, the little head of the match is usually coated with something that makes it more easily able to begin causing a chemical reaction to occur. So let's look closer at the chemical reaction of burning wood. All right, so again, igniting wood, down here we see the fancy chemical equation for wood. It has 6 carbons, 12 hydrogens, and 6 oxygens all bonded together in a single molecule. So it's quite complex. All right, so to ignite wood, you have to start with some complex carbohydrate. In this case, I'm giving you the example of C6H12O6. It'd be different again for the fuel of my match that we were using earlier. But you take that and oxygen as your two reactants. All right, so again, wood and oxygen. And those two things will actually produce carbon dioxide and water. So this is weird. You might not realize it, but the act of burning produces water. Now you don't see it like just dripping off of the wood, right? Because it's in the form of gaseous water. It's water vapor that's produced in the burning process, as well as carbon dioxide. And because of the less complex bonds that we see over here, what that means is you're taking chemical potential energy that's stored here, rearranging it in this new form, and there's now less chemical potential energy with our products, so extra energy is released in the form of thermal energy. But you need some activation energy to get it started, a burning match or some other fuel source to start this process to provide that activation energy. Okay, so again, thermal energy is produced at the end. And my picture's in the way, so sorry about that. But just to show you what this looks like, okay, physically, all right, wood, here's a model of a single molecule of the carbohydrate of wood. Very complex, lots of different bonds in there. Here's a single oxygen molecule, not very complex, just two oxygen atoms bonded together. Here's carbon dioxide, one carbon with two oxygens, and then here is water, two hydrogens and a single oxygen. So again, you can see on the left, this is much more complex, especially with the carbohydrate, a lot more complex bonding than you have over here. And so there's chemical potential energy that can be released in the form of thermal energy as the reaction occurs. So that's just a free kind of introduction to how this idea of thermal energy and heat can work a little bit and where the energy comes from when you're burning wood or coal or other different elements as well. And so this is just one example of a chemical reaction. If you want to learn about others, take more chemistry classes. But I just wanted to start here as an introduction to chapter 7, and then we'll use these ideas and learn more about how and why heat carries thermal energy in different places between different objects and in different ways, and understanding the example of how wood stoves work a little bit, and then how our atmosphere works as well with the greenhouse effect. So stay tuned in the next video for more on thermodynamics.